Alright, what do we do next? Well, just simply following my way through the taskbar here, through the pages on the left-hand side. I'm just adding some properties now for the supports. I've got a whole series of different types of supports that we can assign. I'm just going to use a standard fixed support, but we've got the ability to create springs. We can create non-linear springs where we have defined differences of stiffness over different bands of soil, and as the structure is displated, it will work out the revised spring stiffness. So what am I doing now? Well, we're actually defining groups of areas of structure that are important to us for later on for creating floors. When we define some floor loading, I want to create a series of floors. So here I've got a tool that allows me to define a floor, which I can refer to later on. I simply highlight the bit of structure I want to associate with that particular floor, and later on I can come back and assign properties to these floors. I've created a number of floors here. There's one, there's two, and a third floor. So we can see those floors assigned. With these floors in place, I'll come back to those later on, but here we're going to look at some definitions that are available within the program. I mentioned that there are some auto load generators. The auto load generator is I'm going to use a wind load here, and this wind load I can define either how my pressure varies with height, or we've got a nice tool now to work for the ASCE 7, where we can choose different types of loading to the ASC 95 or the 2002 code, and depending on what type of structure we want to define this as, we can get the program to calculate the forces of the change in wind pressure over height by determining what parameters and what factors to use. And here you can see how that wind pressure will change with height based on the ASC code. So I'm going to take that, and there's my wind pressure profile and defined for me, which I could edit if I wanted to, and also if I wanted to account for exposure conditions, I've got parameters to allow me to do that. I've also got the ability to introduce seismic definitions of UBC and IBC loads. We've also, as I said, got Algerian, Japanese, a whole series of different design codes, and this will create the equivalent static loading based on a distribution of the forces due to seismic conditions, where you simply define the parameters as per your selected code, and the program will identify how that mass distribution should take place over the height of the structure. So we need to define some masses. We're going to just use self-weight on this exercise, but obviously we might want to introduce additional member weights and different weights that we can use as definitions for calculating the masses of the structure. So we're going to go and create some load cases now. These load cases, I'm going to just create a series. I'm just going to step through this quickly. I'm going to create a whole series of different load cases, which we'll start assigning some specific loads to. Each load case can contain any type of loading, and we've got floor loading, and here this is where we're using those floors that we defined, and we can add those in and assign those to the particular floors for the particular load cases. We then take all of these floor loads, different self-weights, different factors, but what about the fact that we were connected up to a different pipe structure? So here I'm picking up a model, the pipe model from AutoPipe, and here you can see that pipe framework similar to the pipe framework we saw in the initial model, and we can take that pipe model and actually start connecting it onto our STAAD model. So we can identify the fact that pipe supports were created in AutoPipe, and we can identify whereabouts they would actually be connected onto our structure, and all of the forces that were generated in the analysis from AutoPipe can be pulled through. So we're going to create a whole series of different connections. Once they're all in place, we can simply go to our tool here to import all of those loads, generate those load cases, including the effect, a torsional effect or rotational effect, due to the fact that the pipes are separate from the pipe, the center of the pipes are sent away from the center of the steel framework. And here you can see it literally takes only a second for it to create all of the additional loads that result from all of the pipe models or the pipe framework and the support information from the piping engineer. And these have been calculated and applied to the structure directly from our AutoPipe model. So define combinations. Okay, here's another great tool that we've added into the program in recent times, which is the fact that we can automatically create combinations based on a rule set from defined from different codes, or you can create your own combination rules and identify which of those rules you want to incorporate. So based on the load characteristics, we can get the program to automatically generate any of the load combinations as defined in those rules. We then, as I said, have a number of different forms of analysis that we can perform. Here I'm just going to simply do an elastic analysis, and here the program adds that command into our data structure. So everything is now ready to run our analysis. We run the analysis, save our file away, and well, this actually took, although it was just a quick snapshot, it's just a second from that analysis. We go to then have a look at the output. It gives us warnings to say that the program was unconnected, but that's not a problem because we know that was the case. But it handled it, it ran the analysis, and we've got information about all of the load cases that have been analysed. Simply drop into the post-processing now. The post-processing identifies all of the different sorts of results that are available to us. Here, for example, we've got a set of displacements. These displacements then can be animated. Also, we can go in and look at the bending moment diagrams or stress patterns on any particular beam. And on that beam, we can see the corner stresses and also stresses along any particular point along the length of that beam. This then gives us a great set of tools for analysis, but then what about design? Well, here I'm going into the AISC Unified or the 36005, where I choose which design, whether I'm working for using the ASD method or the LRFD method. I can then specify any particular parameters for, say for example, the fact that I want to use grade 50 steel or 50 KSI steel, and I could specify buckling lengths, I could specify modifications that needed to be considered for each of the beams. And when I've got all of those in place, I can identify as well a ratio, a fail ratio, so that I can pick out members that are getting close to failure. So with this in place, well, first of all, I need to say which members do I want to have 50 KSI. Well, in this case, I want to assign it to everything. I want my whole structure to be made of 50 KSI. But as I'm sure you're aware, you can change your structure so that you can have 36 or 50 or whatever value you wanted or you had available to you. We're then going to run through a check on that structure to see how that structure is doing in terms of code compliance. So that we take that structure and we run our analysis now with a check code in place, saves the update, and it runs through, this time in 2 seconds. And again, we can run through and see that in actual fact we got what's classed as errors. In actual fact, these are our structure has failed because of slainedness failures. So, you know, if I want to, I can see this graphically, and you'll see that we've got a new tab on our design where we can see a color-coded system where the structure is color-coded based on its performance, and we can either identify it based on a set of predefined lists, or we can identify it clearer for ourselves.